We're going to continue our discussion of acid-base theory today with a discussion of how we calculate pH. Now let's move back a few pages. And we see here a scale for pH. pH, remember, we've talked about pH before. It's simply a scale that we use to measure the relative acidity of a solution, how acidic or basic a solution is. Notice that we've got neutral at 7, and for a solution at 25 degrees Celsius, neutral would be 7. We go from 0 to 14 for our values for pH. Now, when we calculate pH by simply taking the negative log of the hydrogen ion concentration. We've done this with even powers of 10 before. For instance, if we have this number, 1.00 times 10 to the minus 7th, the log of that even power of 10 is negative 7. The value for the negative log then is simply 7. So it's easy to get the pH if we have an even power of 10. We just take the exponent, make it positive, we've got our pH. Notice something about the sig figs for pH. There are 3 decimal places, 3 zeros past that decimal place on 7.000, and that's because of this number right here. That number determines the number of sig figs. And there are 3 sig figs there. For pH values, they are a log function, so we have to remember that sig figs start after the decimal. So that 7 does not count for sig fig place values, those 3 zeros do. So that's why we have 7.000 here. Now, I won't always do that. My general rule is get at least two places past the decimal. And sometimes I'll pay attention to sig figs, sometimes I won't. And maybe I should do a better job on sig figs for this, but on the AP test, 2 places past the decimal has always given us a good value, and a correct value, because they give us 1 place off on sig figs. So we're looking for speed, and we can't spend a lot of time concentrating on how many sig figs we have when we have to do more complex calculations. So that's what it describes here. Also, talking here about how 1 pH unit changes concentration. This is a log function, remember. So every time you change the pH by 1, you change the concentration by a factor of 10. So keep that in mind. Because that's going to be important. If we have a pH of 1, the concentration is 10 to the negative 1. If we have a pH of 2, which is 0.1 molar. If we have a pH of 2, the concentration is 10 to the negative 2 molar, which is 0.01 molar. So you're changing by a factor of 10 every time. That's an important thing to know. It changes a lot when you change that by 1 full pH unit. Other equations. POH then is equal to negative log of the hydroxide concentration. This one's really important because we'll be using it a lot. Anytime you've got the pH, you can find the POH by simply subtracting from 14 and vice versa, because pH plus POH is 14. Anytime we see that little p, that small lowercase p in front of something, it means the negative log of something. So if you say CPK, pKa, pKb, whatever, that's the negative log of that K, or equilibrium constant. The hydrogen ion concentration, then going backwards, if we know pH, we can take 10 to the negative pH value, and that will give us hydrogen ion concentration. 10 to the negative POH will give us hydroxide ion concentration. We can get all of the rest of the values if we know one of those 4. If we know pH, we can get hydrogen ion concentration, hydroxide ion concentration, and POH. So all we need is one value, and that's going to be important to us on several calculations. So look at this first one, this first example. Calculate the pH of a solution in which the hydrogen ion concentration is 3.52 times 10 to the minus 5th. We want pH. We know pH is the negative log of the hydrogen ion concentration, which is the negative log of, in this case, 3.52 times 10 to the negative 5th. If we put that into our calculator, we end up with a hydrogen ion, or excuse me, with a pH of 4.453. Notice something, because this will help us on multiple choice questions when we can't use a calculator. Here's the hydrogen ion concentration exponent. Look at what the pH ends up being. Somewhere in the fours when pH is -5 power of 10. So if pH was a -8 power of 10, then the value, the pH would come out to be somewhere in the negative, so if it was -8, 10 to the -8, then our pH would come out to be somewhere in the negatives, in the sevens. So it drops down one. Again, we wouldn't be able to tell exactly what it would be without a calculator, at least I can't, but we'd be able to find out the range. So that's important. Okay, so the next one, calculate the hydrogen ion concentration of a solution that has a pH of 937. We know that the hydrogen ion concentration, according to our little equations up there, is 10 to the negative pH. So 10 to the negative 8.937, we just put that in our calculator. 10, hit that caret sign, the little rooftop sign, hit negative 8.937, and we get, looks like there should be 3 sig figs because there's 3 places past the decimal. I'm trying to pay attention to it. We should get 1.16 times 10 to the negative, and since this is in the eighths, what would the power be for the hydrogen ion concentration? -9. So try to learn some of those conceptually because, like I said, they can help you out on those multiple choice questions. Okay, so if we've got a 7.88 times 10 to the minus fourth molar solution of HNO3, we want all of these: hydrogen ion concentration, hydroxide, pH, and POH. The very first thing you have to do is decide what you are dealing with and what you've got. This is an acid. It's a strong acid. If we've got a strong acid, then whatever its molarity is, that's its hydrogen ion concentration. I'll say that again since I got interrupted by the bell. Whatever its concentration of the acid, strong acid or base is, that's going to be the concentration of both of its ions. So if we've got 7.88 mole times 10 to the negative fourth molar HNO3, we've got 7.88 times 10 to the negative fourth molar H plus. There's our hydrogen ion concentration. So that's one of the things it asked us for. From that, we can get pH because we know that pH is equal to the negative log of the hydrogen ion concentration. So the negative log of this value is going to be 3.103. So there's our pH. Once we know pH, we can get POH because we know POH is 14 minus the pH. So 14 minus that 3.103 is going to give us 10.897. So now we know the POH. The only thing left for us to find is the hydroxide ion concentration. And the hydroxide ion concentration can be found by taking 10 to the negative POH. Make sure you keep those paired up. Hydroxide ion concentration, 10 to the negative POH. Hydrogen ion concentration, 10 to the negative pH. So make sure you keep those pairs straight. So 10 to the negative 10.897 is going to end up giving us a value of 1.27 times 10 to the negative, since this was a POH of 10, what's our exponent going to be? -11. That's our molarity of hydroxide ion concentration. Okay, one more example. This one gives us a value of 0.00821 molar solution of sodium hydroxide, and it wants us to calculate everything again. Remember, we have to know what we're dealing with. This is a strong base. Strong base means, remember, whatever the concentration of the strong base is, that's the concentration of both of its ions. So this tells us that 8.21 times 10 to the negative third molar sodium hydroxide gives us that same molarity of hydroxide ion. I wish I could get rid of the bells, but I can't, so you'll just have to ignore them. So there's our concentration of hydroxide ions. What can we get directly from that? We can get POH, and POH is going to be the negative log of the hydroxide ion concentration. So that's going to be the negative log of that 8.21 times 10 to the negative third, which is going to give us a value of 2.086. So there's our POH. How do we get pH? We simply subtract it from 14. 14 minus the POH, which is going to be 14 minus our 2.086, which gives us a value of pH of 11.914. So there's our pH. Our last value that we need to find then is our hydrogen ion concentration. And our hydrogen ion concentration we can get from taking 10 to the negative pH, which is going to be 10 to the negative 11.914, which is going to give us a hydrogen ion concentration of 1.22 times 10 to the negative 12. And that's going to be, of course, molarity. And there's our answer for the hydrogen ion concentration.